Hello everybody. So I am going to be starting a new project where we're going to be doing Swerve. So what I'm going to do is I'm going to open folder and go to my Swerve example. And this is a newly created project, and I chose the command robot. Okay, so it comes with a bunch of stuff. Let me just survey this to see what we have. So in the directory, we have the main, which we don't need to touch. We have at the top level robot.java that has okay, so it extends the time to robot, so it's going to be okay. So it has this auton, and here it defines the robot container. Okay, so that's this right here. And inside of here, we have all of our different modes. So we have robot init. This runs when we first, when the robot first starts up. Robot periodic. So what this line does here is this runs what's known as a scheduler. So the idea is that we register all of our subsystems by calling extend subsystem base. What that does is it gives us access to this method here called periodic. Okay, and this code inside of here will run every 20 milliseconds, every loop cycle. Okay, so we have robot container. So here is defined an example subsystem. Okay, so at the top of the robot container, they have an example subsystem. So we're going to be creating a Swerve subsystem. Here they're defining a controller, so we can actually access stuff from the controller. Okay, so those are the two things that the robot container is giving us. This is what's known as a constructor, and this happens immediately when you call the robot container. When you call this new robot container, then what happens is if you go see robot container, this is a special function which is the same name as the class, and this is actually run when you call the new keyword. Okay, configure bindings. What does configure bindings do? So this is where we map the trigger. So a trigger is some sort of event that returns true or false. Okay, so I don't know what this example condition is. Let's see. I guess it's just false, but whatever. And when this trigger returns true, then it runs this command. Okay. And okay, so here's actually where we are mapping the driver controller. So we're taking the driver controller when we call the B button while true. So as you're holding the B button, then you're calling this subsystems method command. Okay, so what does this do? This does nothing. Okay, so let's get started here. First of all, does this simulate? Let's see. Let's check it out. Can I get some light? Yeah, maybe. Okay, so it looks like the simulation is working, but nothing is supposed to be happening, right? Okay. So the first thing I want to do is let's go into Excalidraw for a second. All right, so Swerve Drive. So Swerve Drive is basically, it's a robot that has these Swerve modules. So pretend this is the chassis here. And on each one of these corners is going to be a Swerve module. Okay, So a Swerve module, each module is going to have a drive motor, which makes the wheel spin, like actually go forwards or backwards. The turning, this is what controls the, it makes the entire module pivot. And there's also going to be an encoder. Okay. So the first thing we're going to do is I'm going to create a new subsystem. Okay. This subsystem is going to be called the Swerve subsystem. I'll just call it Swerve subsystem.java. Okay. So here, this is just a regular class. And now, in order to access or to expose so if you go to robot container, I think it's in here. No, it's in robot. This command scheduler, this is called robot periodic. So when every single time, every single loop, this command scheduler runs. And so if you add the word extends subsystem base, then what that gives you access to, again, sorry, I just used my shortcuts. If you right click and go to definition, here you'll see all of the things that this subsystem base will do for you. The most important things that it'll do is should have a periodic. So it exposes this periodic. So what does this periodic do? This method is called periodically by the command scheduler. It's useful for updating the subsystem specific state when you don't want to offload it to a command. Okay. So what does this mean? The first thing I do is I'm going to create this is a constructor. Okay. So this constructor, let me just, okay, and I'm just going to print the constructor is called. Okay. So what I'm going to show you is that I said that this constructor is called whenever we call the new keyword. So if I go into robot container, I am going to create my subsystem, so Swerve subsystem here. I'm going to call this drive, so this is the drivetrain, is equal to new Swerve subsystem. What I'm saying, saying is that this should be called, okay? So let's actually just run the simulation and see. Okay. Now in here in the terminal, you should see the Swerve subsystem constructor. So you see that that's called. Okay, perfect. And now here's where it gets interesting, because we have so a Swerve subsystem, it consists of, what does it consist of? So a Swerve subsystem is just like, is this entire chassis. So it has 4 different modules, okay? And each module has kind of a motor. Like, I can break it down into, this is the chassis, and then inside of here, right, like if this is kind of like a diagram, not a chassis actually, this is a Swerve, this is a module, and there's 4 modules inside. So this chassis is going to have 4 of these modules. So let me actually just right now create that module. I can do it in a different file or in this file. So I can do Swerve module here. Okay. So now I've just created a Swerve module. And now I want my Swerve subsystem to create 4 Swerve modules. So how do I do that? So I need to I have 4 Swerve modules, so create a list of them. Okay, so what does that look like? That looks like this, where I have the name of the variable is Swerve module, and this means it's an array. And an array is just a list of, it's like 1, 2, 3. So it's a collection of items, okay? So I'm saying that I'm gonna create kind of like a container which houses 4 different Swerve modules, okay? And so here is my Swerve module. And now what I'm gonna do is I'm gonna create the Swerve modules, okay? This is actually, Copilot is doing a great job. So what it's doing is it is saying, this is a little complicated, so I'm going to, so Swerve module, front left module, okay? So I am calling this right here the front left module, okay? And we're just gonna start with 1 right now. Okay, so right here, this variable is gonna be the, everything to do with the front left module, okay? So anything related to the motors itself are gonna be handled by this front left module. So the chassis will be able to tell the module to do something, and the module will tell the motors to do something on its behalf. Okay. So here's the front left module. Okay, so now let's start to build out what this module should do. So let's see. This module should contain a drive motor, should contain a turning motor, and it should contain an encoder, an absolute encoder to know what angle the wheel is at. Okay, so it should know about these 3 things. So let's actually figure out how to do it. So again, at the top, we are gonna, well, that's the constructor, but at the top here, we define all the variables that will be needed, okay? So we're gonna need a drive motor, and how we do that is the drive motor is Talon. It's going to be a Talon, okay? So a motor, Falcon 500. So the Falcon 500 motor, so here's the motor, and kind of integrated into this system is the actual electronics that is called the speed controller, and that's called a Talon, okay? So here, this Talon is going to be the drive motor, okay? So we're just defining what this drive motor is. And now we're going to have a Talon called the turn motor, okay? Or the steering motor, I don't know. Let's call it steering motor, okay? So now, how do we tell the Swerve module which drive motor, like which port the drive motor is on? So what we have to do is we have to pass into the Swerve module kind of the port number. So inside of here, we're going to define a few things. So an integer, like a number, drive motor port, and the steering motor port, okay? So what that's going to do, so basically from the point of view of the top level Swerve subsystem, you need to pass in the port number. So I'm just going to call this, let's say 0 and 1. Okay, I don't know what it's actually going to be, but okay. So now I have to instantiate the drive and the steering motor. So how do I do that? So drive motor, is equal to Talon drive motor port. So you can see that what you pass into it, again, if you hover over this, sorry about that. If you hover over this, it gives an explanation. So the parameter, this channel, is the PWM channel that the Talon is attached to. 0 to, okay? So I'm just saying for the purpose of this, simulation, it's 0, and this is connected to the port number 1. Okay. So now I'm gonna do most theory. Okay. So as of this point, right, what I've done is over here, from the point of view of the Swerve subsystem, I can now instantiate a Swerve module where I specify the port numbers, and we actually instantiate the motors. So now we have access to, so when it comes to motors, so let's say the drive motor, when you want to set, here, you can look at all of the different things that you can do, but the most important things that you're going to want to do is set voltage, or I think it's, yes, set. So this set parameter basically is a number from -1 to 1, okay? And so 1 is full speed forward, -1 is full speed back. That's what it is. Okay. So now we have the Swerve module. So now what I'm gonna do actually is, because programming is supposed to be an iterative process, we're actually gonna do some work, and I'm gonna actually show. So this right here is a tool built by 6328. It's called Advantage Scope. We're actually going to start to visualize, this Swerve, okay? So at this point, this is all I care about, okay? So this Swerve module. Now I need to create 4 of them. So I can just do front right module, and maybe the ports on these are 2 and 3. Maybe I can do back left, okay, 4, 5, and back right is 6, 7. Okay. So here are my different modules. Okay, perfect. Now let's actually just let's simulate it. First, let's build the robot code to see if anything is syntactically breaking. Nope, build successful. So now I can simulate the robot code and click OK. And I mean, nothing's going to show up right now, but we're going to get there. Okay. So now what do we want to do? Let's think about this. So we constructed 4 different modules, and now let's actually get it to display over here on Advantage Scope. Okay, so how Advantage Scope works, let's just go to the documentation. Is let's actually figure out how to visualize the Swerve. Okay. So states. So 2 sets of module states can be displayed simultaneously. So there's a red vector and a blue vector, which is going to show the direction. You can also kind of like have the orientation spin, which is cool. So how do we actually do this? The state fields, so kind of the data that powers this visualization, It's an array, which we mentioned earlier, and it's rotation 1, velocity 1, rotation 2, velocity 2, 3, 3, 4, 4, okay? And the rotation is configurable, okay, so it can be either in degrees or radians. The velocity unit should match, okay. So let me actually do something like this. So what I'm gonna do is I'm gonna override the periodic. And what do I want to do? I want to send the data to the smart dashboard. Okay, so let's say, so it's going to be a double, and it's going to be logging state. It's going to be an array, and this is how to. Okay, this is cool. Look at that. So it actually just filled a bunch of stuff in for us. But let's see. How do we build this logging state? Okay, so first of all, I'm just gonna put in some random numbers. So again, it is rotation, velocity, rotation, velocity. So let's say it's 0 degrees in rotation. So 0 degrees for first module. Okay, and we'll see what that visualization looks like. This is the velocity. Let's just say it's, I don't know, 3. This is gonna be in meters per second. Okay, so now I'm just gonna do let's say this is at a 45-degree angle. Degrees is 45, okay? And let's just keep all of the velocities the same, okay? Okay, so this is 8, right? 1, 2, 3, 4, 5, 6, 7, 8. Okay, perfect. So let's just try to log this to the smart dashboard. So we do smart dashboard dot put number array. I'm gonna call this Swerve module states. Okay. And I'm just gonna push the logging state to it. Okay, so what should happen is every 20 milliseconds, this logging state should be pushed to the smart dashboard. So let's simulate the robot code and see if it works. Okay, so the simulation is now actually doing something, hopefully. If we go to Advantage Scope and we connect the simulator, we should see over here Swerve module states. Okay, so hopefully if I drag this in and if the data is formatted properly, you should see something, and we do. So let's look at what's happening. So this is 0 degrees, right? This is the first module. So which one is the first module? So it looks like, I think 0 degrees is relative to the robot's forward position. You can see that I believe this front left is module 0. So 0 degrees for the first module, 45 for the second. So that's this one. Then it goes kind of like counterclockwise or clockwise. So this one is 90. So this is kind of skewed. That's, oh, I think by default this is in radians. So if I go to degrees, this looks better. Wait, what? So this is 0 degrees. 45 degrees, 90 degrees, 135. I think that's right. So how I'm gonna check is I'm gonna make each of these a different speed. I can save that and just refresh. Okay, yeah. So how their system works is this is 1, and that's 2, that's 3, and that's 4. Okay, that's weird. But now we know a little bit more about so it's the front left module, front right, back left, and back right. So this is the order that it should be in. Okay. So, so these are hard-coded, right? But what's interesting is that this value and this value are really the responsibility of the module itself, the first module itself. And this is should be responsible for the second module. So what I'm going to do now is I'm going to do kind of a refactor. And I'm going to put these variables inside of the module states itself. Okay. So this is the angle, and this is the speed. And if we go over here to WPIlib, Swerve state, is it called? Swerve module state. So this is where we get to another kind of like primitive that WPIlib is built. So the Swerve module state class contains information about the velocity and angle of a singular module. This is what we want, right? And this is the velocity, whereas this is the angle. So these really are encapsulated in what's called a Swerve module state. Okay. So let's actually do some refactoring and go into our Swerve module and say that Swerve module state. We're going to call this current state. Okay. So what I'm going to do now is in the constructor, right, I am going to create, say the current state is equal to a Swerve module state. And do I have to pass anything in? If I pass in a Swerve module state with no parameters in there, then it constructs a Swerve module state with zeros for the speed and the angle. So let's actually just write what's called a getter and a setter. Okay, so this is the current state. So right away, I can do a refactor, which is this is going to be, instead of this 0, it's going to be front left module dot, okay. So what I have to do is this current state is kind of like can't be accessed from the outside. For example, if I do dot, I guess I can't access it. Let me force it so we can't access it, because we shouldn't be accessing it from the outside. Private. So if you do private, now if you go over here, you don't have access to it. So let's actually make all of these private, because it's good practice not to like expose the actual things that are internal to the class, expose it to the outside. Okay, so now if I do dot, you don't get anything important here. Okay, so what I'm going to do is I'm going to create a function called public Swerve module state get state, right? So what this is going to do is this is a function called get state. It's a public method, so things from the outside can access it. And what it's going to return is a Swerve module state. And that's just this internal variable here. So what does this mean? Now I can do dot get state. And on here, I can access the angle and the speed in meters per second. So again, this is the angle, and there's a get degrees method. Yeah, I guess so. So here, look, so that replaces this 0. Now, to get the speed of the front left module, I can do front left module dot, and it's the same thing, get state dot speed in meters per second. And now I can just literally do the same for the rest. And this is GitHub Copilot that's filling this all in. So what this should do is, if I refresh the simulation and I go back to Advantage Scope, you'll see that, look, well, you'll see that it updated here. The arrow doesn't show because the speed, right, is defaulted to 0, so the length of the arrow is 0. But this right here, this wedge, shows the angle. Okay. So for example, hold on. Okay. So for example, let's say I initialize it with a speed of 1 and an angle of let's say degrees to radians of, I don't know, 30. Okay, I'll get into this rotation 2D thing later. Let's say we refresh it. So all of them, remember, this is in the constructor, right? So all of them will be initialized in this way. So you can see now okay, so I'm back, and I don't exactly remember where I left off. However, so I think we were at the Swerve module state. So yeah, so if we look over here, yeah, this is where we were at. So right now we have the ability to, okay, so each Swerve module now has the ability to return its current state. And that's in what's called the Swerve module state, and that encapsulates the angle and the speed. Okay. So this is nice. Let's see where we should continue. Hold on. Okay, so I got some coffee and I'm good to go. So now I believe the next thing to do that we want to do is let's figure out the next step of the puzzle, which is Excalibur. So now we have these modules going, but we're kind of like setting them to whatever speeds here. Or like they're just an arbitrary angle that we're setting. So what we want to do now is, okay, so we have a text. So now what we want to do is we want to figure out a way to take the joystick values and somehow go through this, we'll call it magic for a second, and convert that into Swerve module states, right? So we don't actually want to set the Swerve module state for each of them, specify them directly. We want to go one step higher in abstraction and be like, okay, so we have a joystick, right? And let's say if you have I guess it's not a joystick, it's a controller, but let's say I have this, and I take a picture. Now let's go back to Excalibur. So let's say I have a joystick, okay? Ooh, that's silly. Okay, and how are we going to translate the joystick into, can I draw on this? Yeah, I can, that's cool. How can I translate the joystick actions into Swerve module states? So what we're going to do, I think, is we are going to bring this up here. And let's just say when we go up and down on the left joystick, that is going to make the robot, let's say, go up. So this is the forward, so it's going to go forward. And if we go that way, it's going to make the robot go that way. Okay, so just by a single controller here, or a single joystick, we're going to control the strafing. So right now, we're not going to handle any turning. So let's actually figure that out. So in order to do that, right, so this is controlling what the chassis should do, not what each of the individual components should do. Okay, I guess, yeah. So what we do is this magic here is what we call kinematics. And let's go to kinematics, okay? So there's kinematics here. I guess let's go to the definition. What is kinematics? The brand new kinematics suite contains classes for all of the different types of drive. Differential drive, which is West Coast drive, like tank drive, Swerve, and Mecanum. Okay. The kinematics class helps convert between what's called a chassis speed object, which is going to be very important, and which contains linear and angular velocities for the robot for a robot to usable speeds for the individual types of drivetrains or the motors. In the case of differential drive, it's the power of the left and right wheels. And then for Swerve, it's the individual module states. So the chassis speed object, again, it's what we want the robot to do at a high level. How fast we want it to go forwards, backwards, left and right, and how much we want it to be turning. Okay? So that's kind of like what we desire to do. So the joystick is going to map to this chassis speed, and we pass it through this Swerve drive kinematics thing, and then it spits out what each of the motors should be doing. Okay, so let's go over the chassis speed object or class. So this chassis speed object is essential to the new WPI kinematics and odometry suite. Odometry is what we'll get to, which is like your robot knowing where it is on the field. Okay, so chassis speed represents the speed of a robot chassis. It has three components: Vx, Vy, and omega. So what is the Vx? So Vx, it's kind of strange. We think of x as left and right, but in the case of how we're defining it here, x is the forward or backward direction. So if we go on, if if we have a robot here, this is the positive x direction, so forward and backwards. Let's go back to here. And Vy is the velocity of the robot in the sideways direction. Positive values means it's moving to the left. Okay. So here, this is the plus y direction. So if I want the robot to be moving forward, so this joystick is only forward and there's no left or right, the Vx is going to be like a positive value. Vy is going to be 0. If I move this down, Vx is going to be a negative value and Vy is going to be 0. If I turn left and right, if I turn left, it's going to be positive y, and so on. And a combination. So if you have, let's say, new chassis speed. Okay, if I have, let's say, 2, 0, 0. This means move, let's say, 2 meters per second forward. Okay, just to give some examples. Now if I have -2, just move 2 meters per second backwards. If I have 0, 2, this is 2 meters per second left, and so on. Okay? And then if I do like 2 and 2, it's going to be move north, northeast, I guess, at I guess it's 2 meters and 2, so that's 2 times square root of 2. 2.82 meters per second. 2.82 meters per second. Okay? So these are some examples of the chassis speed. But right, if I want to move northeast at 2.82 meters per second, that is what I'm going to feed in the chassis speed. But then the question is like, well, okay, that's all fine and good, but like, what is this front left drive motor? What is it supposed to do? What is the turning motor supposed to do? Which way is it supposed to face? Right? So in this case down here, this is actually, the robot is going to be going like this. So the turning motor needs to be kind of turned at like this, right? So what is supposed to tell this turn motor what to do? And that's what the kinematics is supposed to do. Okay? Constructing a chassis speed object. We just went through it. The constructor for chassis speed is very straightforward. It accepts Vx, Vy, and omega. Okay, Vx and Vy are in meters per second, a speed. Okay, and this is how you do it. Good. This we'll get to later. This is going to be very interesting, but we'll get to that later. Okay, so great. So first, let's go into how we actually construct the swerve drive kinematics. Okay. So again, the kinematics takes in a chassis speed and it spits out a swerve module state. If you'll remember, this get state here, this is a swerve module state. So really what's going to come in is a chassis speed object, and several swerve module states are going to come out of it. So you'll see that we're actually going to override this current state kind of with what comes out of the kinematics. Okay. So we already went over that. So let's construct the kinematics object, okay? So FRC control tab something, tab sys. So I'm not going to get really into the map, but I want to just give like a quick picture overview of how this thing works, of how this kinematics works. Okay, so this is a very amazing kind of like compilation of all of the different control system related stuff is in there. Is well done, and can be done, and a lot of this is what created WPI-lib's functionality. So if I go to differential Swerve, I think. Swerve drive kinematics. Okay. Perfect. Again, I'm not going to go too much into the math here. But let's see. No, that's okay. Really, it's just this. So basically, the core components, right? So you might logically understand that if you have a robot that's a square, right, where each of these modules are in a square, versus if it was like super fat and the modules were on the ends, the way that like the front right module should handle kind of like, you know, should help the robot get to where it wants to go would be different. So it's very much dependent on versus, right, if you have a long robot, right, and these are different options. So the first thing we have to do for Swerve drive kinematics is we have to give the code, we have to tell it kind of what are the geometries of our robot, okay? So the Swerve drive kinematics class, which is what we care about. This is the black box, which converts the chassis speed to Swerve module states. Yeah, the kinematics, okay. So it accepts a number of constructor arguments in the constructor, with each argument being the location of a Swerve module relative to the robot center. Okay, and it comes in as what's called a translation 2D. Okay, so the number of constructor arguments correspond to the number of Swerve modules. Okay, relative to the center of the robot. Okay. So, positive x represent moving toward the front of the robot, whereas positive y is towards the left. Okay. So this is the chassis speed. Now let's talk about the translation 2D. Okay. Let me take these, group them together. Let's just move it over here and shrink it a little bit. So at least we have that. Okay. So let's say we have the center of the robot. What we have to do is we have to say from the center of the robot, line, dotted line, how far this module here, how far over in the y direction is it? Right. This is the y direction, and how far up is it in the x direction? Okay, and we have to basically tell the kinematics where each of the modules are relative to the center. Okay, so we are going to assume, actually, we go over here and we go to the Swerve drive that we're programming. I'm gonna assume it's a square. Okay, so it's like a square. So what does that mean? Let's actually go into our code and actually get started. So the kinematics object is not a responsibility for the Swerve module, but it's kind of like a property of the overall subsystem. So here we are actually gonna define a kinematics object. Again, takes chassis speed and returns Swerve module states. Okay, so it's, I think, Swerve kinematics right here. So I'm gonna call this kinematics, okay? And okay, I guess. Oh, okay, fine. So I'm defining it up here. Okay. It's not the best thing in the world, but okay, fine. Equals new Swerve drive kinematics. Okay. So here it wants us to pass in translation 2D objects. It's actually giving it to me. So I'm gonna hit enter and I'm gonna import that. So let me show you how to import it. So if you right click here, actually if you hover over this and quick fix, import translation 2D, it'll import it over here. Or you can just do import. You can just start typing in translation 2D and it auto completes. Okay. So now what are all of these? What is all this? Okay. So let's see this translation 2D object. Okay. So the X component and the Y component of the translation. Okay, so I'm actually going to create another variable called chassis width, and I'm going to say this is, well, first of all, we want to look in this kinematics, and I believe it should be passed in as meters per second. So let me go back over here. See, this is 0.381. Yeah, I believe this is in meters because everything is in meters. Okay. So let's say I know that the chassis is 32 inches, right? Inches is 32 inches wide. And let's say the double is, the length is 32 inches wide. It needs to be in meters. So if I want to represent this in inches, but I need it to be converted to meters, there's a units class. So if you type in units dot, here's a bunch of different conversion ratios, which are very nice. So I can just type in inches to meters here. So what I can do here is I can pass in 32 inches, but it will convert it into meters. Just like that. So now, now that I have the width and the length, and they're both the same because it's a square, now what I have to do is I have to call, let's translation 2D, I'm going to say the front left location. Okay, this is very nice. Oh, it does this. So what this is doing here is it's creating a translation 2D object. In translation 2D, if we go into it, it basically just allows you to specify the measurement in the x and the y direction. Okay, and so this is the x direction and the y direction, and let's just make sure that we're getting the distance is correct or something, like x is correct. So positive x value represents moving towards the front of the robot. So in the picture, it's this vertical displacement. So this is the length, and this is the width. So x is the length. So let's make sure that we got it correct. So the x is the length. So this is actually the length, and this is the width, okay? Now let's make sure our signs are right. So this is a positive value and a positive value for the front left location. Front left is this one. The coordinate system is positive and positive. So this is correct. So the front right will have a positive x and a negative y. Okay, let's see if positive x and negative y. Perfect. So now we're going to do translation 2D, back left. This is going to be negative x, yeah, and positive y. Yep, GitHub Copilot is on point. Perfect. So now these are the defining the location of the wheels relative to the center of the robot. Perfect. And now we can actually okay. Maybe like this. So now now we're able to define the kinematics object. So now what we need to do is we need to pass in these locations. And they should be in the same, well, I guess, okay, fine. So what we're gonna do is front left, front right, back left, back right. And the order of these don't matter, is like, because what's gonna happen is this kinematics, when it gives us the swerve module states, it's going to be in the same order that we've supplied the location. So it doesn't matter if we like swap these, but we have to stay consistent. But because the advantage scope keeps it in an order like this, and then this, and then this, and then this, we'll keep that same order here. Front left, front right, back left, back right. Okay, perfect. So now we have the kinematics object. Now let's go back to the documentation and see how it's used. So we've done this step. So now we need to convert the chassis speed into module states. Okay, this is where it gets fun. Because what we can do is, let's define a method called public void, and it's going to be called set chassis speed. Okay, and what it's going to do is we're going to be passing in a chassis speed, desired speed. Okay. Okay. So I'm just going to call this desired. This is what we want it to do. Do I have to put a semicolon? No, I don't. So what I'm going to do is I'm gonna use this kinematics object. Well, I guess they're doing it all for us, but I'm gonna get the Copilot is like on point here. So I'm gonna call this kinematics object and do dot. It's gonna say to Swerve module states, okay? So this is the function which converts the desired chassis speed into module states. And I just realized that Swerve module states new states. Okay. I think, isn't this actually no. Okay, so what I've done here is I'm passing in the desired chassis speed. What comes out, as you see, is an array of Swerve module states. Okay, and it's in the same order that we pass these locations in. So what happens if we literally just go, so new states, I'm gonna take the first entry, which corresponds to front left location. Again, first, hold on. If you want, so it's in 0 index, so the first item is 0. It's kind of strange, but now what we want to do is we want to tell the Swerve module class right here, we actually, instead of just getting the state and it's like just you know, as it is starting out, we actually want to set the state. So what this is doing here is it is saying, okay, if you give me the new state, I'll update my current state to the new state. So what does this mean? If I go here and I say front left module dot set state, if I pass it in new states at 0, the first item, then I will be setting the front left module to this state. And should be auto completing it all for me. Perfect. Uses fancy map. Okay, now here I'm going to set the state of the modules of each module. So this is the speed of direction. Okay, and that's it. So if I just call the set chassis speed object, now I don't even have to worry about the actual individual module, like the speeds basically. This handles it for me. What I do need to worry about is this chassis speed, which is great. So now comes the moment of truth. Now what I need to do is, what's the best way to do it? I'm gonna do it, I don't want to introduce commands right now. I just want something quick and dirty. So what I'm gonna do here is I'm gonna be passing into the Swerve subsystem the M driver controller. So now the Swerve subsystem will know about the drive controller. Okay. So first I have to pass that in. So Xbox controller. Now here this is get a reference to the controller. So Xbox Xbox controller. So here, can I do that? No. I'm gonna call this IO for input output. Cool. So now I have access to the controller. And now in my periodic, this is where I'm going to get the read data from the controller. So I need to get the X and Y values of the left joystick. So if I do controller dot Y, get left Y. Nice. So I'm gonna get so what I'm actually gonna do is I'm gonna create chassis speed, so my new desired speed here, and again this chassis speed is gonna be the dx, dy, and d theta. How fast I want to go on the x, on the y, and on the theta. Theta is turning. So for now, so the x is going to be, well, x is forward and backwards, so I want the get left y. This is get left x. This is going to be, yeah, perfect. So this says, pushing forward will ask the robot to move forward. Pushing left will ask the robot to move left. Yep. And this is pushing left will ask the robot to rotate left. I think this works. Now all I need to do is I need to call set chassis speed with the new desired speed. And I think this should work. Okay. Oh. Let's see. The constructor Swerve subsystem command Xbox controller is undefined. I thought this is an Xbox controller. Okay, so it seems like this is called a so I guess what's being passed in is a command Xbox controller. I don't know what that is, but that's fine. So here, I'm gonna, okay, why not? Okay, but then, does it still have, okay, so it seems like everything is working. If I go here and I go to build robot code, it's gonna just build it to see if there's any errors in building the code. Okay, it's all good. So if I right click and go to, oh no, I need to go up here, simulate robot code, it should work. And because I don't actually have a controller, I'm gonna need to like play around with this for a few minutes. I think there's a joysticks Xbox controller. Okay, I don't know how to do this necessarily. Xbox controller, fine. Oh. It's not maybe IntelliOut whatever? No. My thought is that oh, maybe I need to connect. Searching, okay, it's connected. Oh, maybe that's not the axis. Hold on. Get left X. Get left. Hold on. So I need the left Y and the left X. Okay. So left Y is 1. Okay. Left Y is 1. Left X is 0. Okay, so I'm doing the left. So how am I gonna debug this? What I'm gonna do is I'm going to go in here and say, maybe I can just like, print the new desired speed. Does that work? Can I print it? Yes, I can. Okay, so let's actually just see what this is printing now. Okay, so zeros. Oh, keyboard, joystick. Okay, so this is perfect, right? So I guess this is inverted. So I'm pressing the down button and that's making it go X. So, and if I do that, okay, so that's fine. So now let's actually see. Okay, so something is working. I think the joystick mapping might be like inverted. That's okay. So now I'm gonna go over here. I'm gonna go to the swerve, and if we did it properly, maybe we didn't. Yeah, look at that. So what we're doing here, okay, perfect. So I'm just going to keyboard 0. I am going to, this is SW, W, clear. Cool. So now if I hit W, it goes up. Okay, so D and A are flipped. So that's A, no. That's A. Cool. So now, perfect. Look at that. So if I go forward, you'll see that all modules are being told to go forward. And if I go left, all modules are told to go left. If I do both at the same time, they're told to all go at the same time. So you'll see something that they're all mimicking each other, right? And because if you're just strafing, if you're going forward, backwards, left, right, without turning, they all should be doing the same thing. The math gets interesting when you want to turn as well. And let me get that. So I need to get the right X, figure out which, so that's 4. Okay, so what I need to do is add I think it's this axis here. Let's do J, and L, maybe, I don't know. Let's try. So if I do J, perfect, yeah. So if I want to rotate, right, so spin clockwise, I'm gonna go on the left X. So you'll see here, in order to rotate, just spin in a circle, you'll see that all of them have to be pointed at kind of like 90 degrees from each other. If I go right, it's 90 degrees the other way. But what's interesting is if I want to go forward and rotate, you'll see this is where it gets like crazy, right? So this is what the kinematics object does. It takes your desired speed. I'm saying I want to go forward to the right and I want to be rotating. And it'll do the math for me. See that? To be able to know where to, what the direction should be. And this is basically Swerve Drive. We have it kind of simulated in here. But this is only the kinematics, okay? So this is the first big accomplishment. The second, and I don't know how to do this in simulation so well, is the idea of okay. So if I want to tell the robot to go at 5 meters per second. So I want to tell, now we're looking at the individual. So what we're doing now is we are looking into this Swerve subsystem, okay? And specifically, the Swerve module. Specifically this set state, okay? So let's pretend I'm talking about just setting the speed, the wheel speed for a second, okay? Imagine currently you are at rest, okay? I guess this is kind of like the, where you are now. Your robot, maybe that's not the best way to do it. Let's do a line. So let's say your robot right now is at rest. It's not moving. And you tell it, I want to go 5 meters per second. Well, hold on. Kinematics. Yes. You tell it, I want to go 5 meters per second. The thing you're actually doing, right, when you say tell motor to go forward, what are you doing? You are setting a voltage. So it's like you're setting the power to the motor. So right? So just like the chassis, the kinematics was able to go from something that we care about, which is what the robot should be doing, to kind of like what we don't really care about, but what the robot cares about, which is, okay, for each of the modules, what's happening. okay? But now that we're able to tell the robot at a high level what we want it to do, and it will figure out the rest, now we have to go a little bit deeper into the Swerve drive, into the module itself. Why? Because when you tell the module what we care about, right? Here. This is a good way of representing it. This black box, this kinematics thing, is able to convert what we care about into what the robot cares about, okay? And this is a lot of programming just in general. It's like we care about something, the computer cares about something else, and this black box handles that for us. So now, let's actually kind of expand upon that. What we care about, what the robot cares about. But we can say that this is also kind of what we care about, because what the robot really cares about is the motor power or voltage, okay? So if we follow the same analogy, we have a black box, which we are gonna do this like translation, right? So this is what the robot cares about, but also like not exactly what the robot cares about. So this is the speed of wheel and the rotation of wheel. It's the rotation speed of wheel. No, it's not. It's the rotation angle of the wheel. And what the robot needs to do is it has to figure out what power do I need to send the motor to get to this speed of the wheel. For example, let's say we are at 1 meters per second, okay? So we're going slow, but we have to go faster. We need to send positive power to motor, okay? So at this stage, we need to send I'm gonna do positive voltage to the motor, okay? So we need to do that for some time. And then that's gonna make the robot go faster, you know, and maybe now it's at 3 meters per second, I don't know. And this right here is time. So now, if we reevaluate, we're at 3 meters per second, but we need to get to 5. So we are gonna need to send positive voltage to the motor. That's gonna cause, let's say, the motor to go here, up until 6 meters per second. So now it's going too fast, right? Because we wanted it to go 5, but it overshot it and it went to 6. So at this point, we actually have to send a negative voltage to the motor. Okay? Is that actually what we're doing? 5. Well, it's not a negative voltage to the motor, but we have to go down in our voltage. We have to go down in how much power we're sending it. Okay? So what that's going to do is it's going to have it come closer. And so what the robot is doing is there's going to be this black box here is some process that takes us from what the robot cares about, which is the speed of the wheel and the rotation angle of the wheel, to what the robot really cares about. At the lowest level, what do I send to the motor? And this right here is something called PID controller. Okay, it's a huge topic in and of itself, and maybe PID controller FRC. Let's see how WPI-lib handles PID. Okay. What is a PID controller? The PID controller is a common feedback controller consisting of proportional, integral, and derivative. P, I, and D all stand for something. Hence the name. This article will build up the definition term by term, while giving us some intuition. Okay, so first we'll get some nomenclature out of the way. So the term reference, so in our example here, this right here, our desired speed, is what we call the reference, or a set point, the desired state of the mechanism. The term output or process variable is where we are currently. So where we are currently, what we're actually measuring, this is called the reference variable, the process variable. This is what we're measuring. And what we're doing is we're trying to bring the process variable to the set point. Okay. Let's see if it's even good. Let's just start with a proportional term, okay? So there's an idea that if you're at 1 meters per second, you have to like boost the amount of power that you send to the motor a lot. But if you're at 3 meters per second or 4 meters per second, the idea is like you're almost there, so don't overdo it. Right? Don't go and send the same amount of like increase in power to get to this, to get from 1 to 5, whereas you're closer. So send a little bit more, but not too much more. And this is what the P stands for. This is proportional. Right? What we're trying to do is we're trying to tell the robot how much power to send to the motor. And so the idea is like, you should send enough power, you should send only a power that's proportional to the distance you are away from your target. So if you're super far away, send a lot of power, that's great. But if you're close, send a little bit of power. So they define the error term as kind of the difference in these two values. So the proportional term attempts to drive the position error to 0, right? To get this white to this blue. And if that error is 0, that's what we want to do. And so how does it do it? It contributes to the control signal proportionally to the current position error. That's exactly what we said. Intuitively, this drives and moves the output towards the reference. Okay? So this, this doesn't make so much, whatever. Yep, so that's basically it. I'm not going to get into the D and the I right now. But basically, like here, this yellow is a set point, and the blue is a process variable or the output. You can see how over time the system will respond. And the idea behind a PID controller is that P is a number that you tune. You have to specifically tune it to the robots to make it act as expected. So how does this work? The PID controller class in the FRC namespace is deprecated. Oh. Should use the one in FRC2. Java should use it. Okay, I'll put that. While PID controller may be used asynchronously, it does not provide any thread safety. Okay. Okay. So this is how you create the PID controller. You just do PID controller. This is the name of it, which is PID. This is new PID controller, and here you just set in the P, the I, and the D values. So these are numbers, and for now you can just say I and D are 0. And this P is something you have to tune. Okay, that's fine. So how does this work? So once you've created the PID controller, what you have to do is you have to calculate the output of the PID algorithm. What does that mean? Calculate the output of the PID. Okay. So basically, right, what is the PID doing? It needs to take in where we are currently and what our target is. Okay. So you'll see that this function called .calculate is taking in where we are currently. We read it in through an encoder, and here's where we want to be. Okay, and then here we set it. Then we say this motor actually set this as the power. So this should start to make sense. Okay. Yeah, we don't need to do any of this. Yeah, we don't need any of that. So we're going to be using this in the code. And where are we using it, right? So I gave the example of wheel speed, but the same idea goes for the angle of the motor of the wheel, right? Because the idea is, let's say it's currently straight, but it needs to get to 90 degrees. So we have to tell the motor to turn, the steering motor, we have to tell the motor to turn, provide some sort of power in order to get this wheel to turn to the set point. So this red is the set point. But the idea is that, like, same kind of thing, right? This wheel could start here. And I gave it a lot of power because it's super far away. It's 90 degrees away. So I'm gonna make it go like this, and then it's gonna go, oh, oops, I overshot that. So I go back, and it's kind of like in this constant process of like making sure this wheel is exactly where it needs to go. And if you set the P for, incorrectly, it'll actually, when you ask it to go 90, it'll go like this, and it'll just like wobble. So that's where you have to, like, quote unquote tune the PID. So back over here in the Swerve module, we actually need two two PID controllers. Why do we need two? Because PID controller So we need one for the drive to make sure that the speed is correct, and one for the steering. Okay, and these are both gonna be these are both gonna be two PID controllers. Okay, so what do? Is in the constructor we have to initialize the PID controllers. Okay, well these aren't so good. So I'm just gonna hard code this P to be, I don't know, 0.1 and 0.1. I don't actually know what these P values are because I haven't tuned it yet. But now that we have the PID controllers, right? We have to modify this set state because this is actually kind of lying to us. So what do? So this is the set desired state, right? This is what our desired state of the module should be. And I'm actually going to create another variable. Swerve module. Thought I already did this, no? Swerve module. I did. Oh, oops, sorry. This is the constructor. So I'm actually gonna have this is what my current state is. And swerve module, and then I'm gonna have a desired state, okay? So, this is now, hold on. So this right here, set desired state, this is perfectly fine, right? Because we can say, okay, we can update at any time what our desired state should be. But we can't just say, oh, my current state is now this, right? Because there's this physics involved, like when it comes to the wheel speeds, there's physics, there's the weight of the robot prevents it from going, to getting there faster or something like that. So what we have to do now, and this is where on the robot, you literally just call the encoder. Oh, oops. So now we need something else, right? Because in order to know what this value is, we actually have to read the encoder, right? Read from a sensor. And this is where I'm gonna struggle a little bit, just because I'm not so familiar with the encoders. But in simulation, right? We don't actually have the robot to provide us those sensor values. And this is where there's something called simulation. Robot simulation. Physics simulation. Okay. So, here, look. Because basically what we have to do in code somehow is we have to model we have to simulate the physics that's actually going on. So when there's a deviation between our current state and our desired state, like our code will be able to say, oh, there's gravity going on, or oh, there's like this momentum thing going on. So this is where I don't know exactly how to perform this simulation, and this is where I'm gonna need to do some research, and I may have to unfortunately stop the video to understand how to get this to work. Okay. Mechanical advantage. I think my internet is not doing so well right now. Yeah. Let's take like a few minutes to try and figure this out. So they do a lot of simulation stuff, and they actually simulated their subsystems, drive, module IO sim. Yeah, here. So here they have, okay. So what they're doing is they're simulating their drive, their drive as a flywheel. That's interesting. And they're simulating their turning, so they're steering as also a flywheel. Okay, so these are the models that they're using. And the idea behind flywheel, oh, okay, that kind of makes sense. Yeah. That's interesting. Flywheel sim. You know who has a good thing? It's not really a stretch, but it's interesting. So the idea of a flywheel, right? No, that's an elevator. Flywheel is that, yeah. So basically this is like the characteristic of the motor. So this is like a way to represent a motor. Here's a gear ratio. And like a flywheel is like a shooter, right? There's a big mass, you know, in the case of a shooter, it's like there's a big wheel that you're like spinning up to speed. Whereas with a drivetrain, right, when it's going, that momentum is kind of like this, the same momentum as this flywheel spinning. So that's interesting. Okay, so I'm just gonna steal what they have. Let's see how they do it. So, turn ball to position. Okay, so here they update the simulation. Here, okay. So here they get, okay, so here they are figuring out somehow. Okay. Okay, got it. So what they're doing is, okay, so they update the simulation, so they run the physics, and then what they do is, this is what they're measuring. So this is kind of like their sensor, right? And the sensor, what is it doing? Saying get angular velocity radians per second, and they're multiplying it by seconds. Okay, so this is like the loop time. So what are they doing with this though? They are, okay, so they're just saying, okay, so this is the amount I need to, okay, so in this past 20 milliseconds, this right here is how much the motor sorry, how much the wheel has spun. So they're adding how much the wheel has spun. Okay, and what are they doing? Well, the turn absolute position radian is less than 0, so they're adding 2 pi. So they want to get this to be like between 0 and 2 pi. And then while the turn absolute position is greater than, okay, fine. So they're just basically making this absolute position radians between, if it's below, if it's like negative, then they bring it up. So it's within 0 to 2 pi. And then here, if it's like 10 pi, then they bring it down. Okay. So that makes sense. So that's to get this turn absolute position. Drive position radians. Okay, so this right here is handling the turning. So it's handling this. And this, I think, is handling this. Okay. Okay. Drive sim, get angular velocity, okay. I'm sorry, I got tired. Okay, so I guess let's just start. Let's do the turn sim because that's easier. Okay, so we're gonna do the simulation. Okay, I'm just gonna copy their work. That's completely legal. It is. Okay, so I'm gonna do the flywheel sim. I call it steering simulation. It's equal to new flywheel. And here, I'm not gonna go over all this. Get Falcon. So it's gonna be 1. Okay, so I need that, and I'm just gonna copy their 150.0 divided by 7.0. And what is this value here? The third value is the gearing. Okay. And meters, gearbox, gearing. Oh, okay, so the second parameter is the gearing. Okay, got it. So this right here is the gearing, and this is kind of the what's it, inertia, I think, or something. Yeah, it's a moment of inertia. Got it. Okay, so steering sim. So how do I? Okay, so I have the simulation. So what I need to do, okay, so I have not done anything to set the current state. Okay, so what am I supposed to do? So public void, so I should do a periodic function. So this should run every 20 milliseconds, okay? And what am I, what is it? This is crazy. That's crazy. No, I'm not doing that, but that's very good. Whoa. Nope. Okay, so what I want to do is I want to first, what do? They run a simulation. So this is steering sim dot update and 0.02. Okay, because it updates every 20 milliseconds. So this kind of like advances the simulation in time. Okay, so now what do I need to do? Get the new simulated angle. Okay, so double simulated angle is, so simulated angle change since last time. Okay, so how do I do that? I do steering sim dot angle diff in radians. So steering sim dot get angular velocity in radians per second. And I'm going to multiply that by my loop period. Okay. So now what I need to do is turn relative position radian. Where is this at? Drive. I'm doing this turn. Turn position. Okay. Okay, what am I doing? So now what I need to do is set new angle. But where is this used? Turn. Okay. Oh, got it. Okay, so after I've done this, now what, okay, got it. I think I understand. So now what I have to do is now this right here is how much my angle has changed. So what I need to do now, this is in radians. So now I need to take my current state. So current state dot set, no, hold on. Can I basically want to create, oh, okay, I know how to do it. Yeah. Okay. So what I have to do is I have to take my current state and I'm gonna set that equal to, I'm gonna update current state. So how do I do that? So that's gonna be a new Swerve module state where the first parameter is the, oh, I think this is what I want actually. Nope. How do I? previous. I think this is what I want. This kind of makes sense here. Swerve module state. Speed and angle. Okay. So it just got the set the new speed, set the new angle. That makes sense here, kind of, maybe. From degrees. So this is radians, so radians to degrees, like this, maybe. This updates the current state. But I don't have anything to do with the PID controller. So where does that come in? Because, oh, I don't have, wait, what? Maybe in the oh, maybe in the huh? Okay, so maybe in the simulation I don't have any PID controller. I don't know, I'm just gonna try this. What's the worst that can happen? That's pretty bad. What's it say? Oh, I think. I deleted a. Got it. Okay, I'm starting to understand this, I think. Let's see if it does something. So let's now bring up Advantage Scope, connect to the simulator. Okay. Teleop. Nothing happens. Okay, I think I'm gonna call it quits here, but I don't know how to necessarily do the simulation, so I'm gonna end here.